Okay, let's dive right in. There's this quiet revolution happening in science. It's changing how we understand everything from genetics to marketing. But there's one key field that's been almost entirely left out. We're talking about a new way of thinking about data, one that promises much richer, more intuitive, and way more powerful insights. And this quote from the psychologist Jacob Cohen, man, it just perfectly nails a huge problem, a problem that's been at the heart of data analysis for decades. For pretty much a century, we've been leaning on a statistical tool that feels like it's giving us the answers we want, but it's not. It's actually answering a completely different and frankly, a much less useful question.
0.4%. That's the tiny, tiny fraction of over 10,000 studies in the organizational sciences, published over a whole decade, that use this newer, more intuitive method. We're talking just 42 articles out of more than 10,000. So what is this old method that's got everyone in a headlock, and what's this revolution that's trying to replace it?
All right, to really get what this revolution is all about, we have to look at the reigning champion of statistics for the last 100 years or so, the p-value. It's the absolute bedrock of something called null hypothesis significance testing, or NHST, and it has totally dominated scientific research for generations. You've definitely seen this before. P is less than 0.05. It's treated like some magic number, right? Like a secret code that separates a real effect from just a random coincidence. It's basically the golden ticket to getting your research published. But here's the thing. It has this fundamental, really counterintuitive flaw that messes with everything we think we know.
And this right here, this is the core illusion. The question we all want answered is super simple. Hey, based on the data I just collected, how likely is it that my theory is right? Makes sense, right? But that is not what a p-value tells you. No, it answers this bizarre, totally backwards question. Okay, let's assume my theory is completely wrong. How weird is the data I just saw? You see the difference? It tells you how surprising your data is, not how likely your hypothesis is to be true.
And that brings us to the challenger, a way of thinking that honestly lines up way better with how we all naturally learn about the world. It's called Bayesian analysis, named after Thomas Bayes, a statistician from way back in the 18th century. And it's not really a new thing so much as it is a return to a more logical way of dealing with evidence.
So instead of a simple yes or no, significant or not significant, Bayesian thinking treats probability as a degree of confidence. It's not about passing some magical test, it's a process. It's about constantly adjusting how confident you are in an idea as you get more and more information. It's this really beautiful, logical three-step dance. First, you start with a prior belief. Basically, what does the evidence already suggest? Then you go out and collect your new data, and finally, you combine those two things to get a posterior belief, which is just a fancier way of saying your new, more informed, updated understanding. You're just reallocating your belief based on what you just learned. Sherlock Holmes, of all people, totally gets this. It's just common sense reasoning. Think about it. If you have two suspects for a crime, and new evidence points strongly to one of them, your belief that the other one did it naturally goes down, right? As you rule things out, your belief in what's left gets stronger. Well, Bayesian analysis is just the formal, mathematically correct way of doing exactly that. So what does this actually look like when you do it? Well, the real power of Bayesian analysis becomes super clear when you put its results side by side with the old method. So let's take an example from the research. Say we're trying to predict an employee's job performance. We'll look at three things: their general mental ability, or GMA, their level of conscientiousness, and their biographical data, or biodata. The old way, the frequentist method, with its p-values, it just spits out one number. It might say the effective GMA is exactly 0.24, period. It seems really precise, but it's actually hiding a ton of information. The Bayesian approach, though, it doesn't give you one number. It gives you the entire landscape of possibilities. It shows you a full distribution of the most credible values. So instead of just one answer, you get a full probability distribution that looks something like this. This is what's called the posterior distribution. The peak shows you the most likely value for the effect. But, and this is so important, it also shows you the whole range of other plausible values and tells you exactly how much you should believe in each one. You see all the uncertainty and the certainty at the same time. And you get this rich, nuanced picture for every single factor you're looking at. So in our example, the analysis might show that, yeah, GMA has a strong and pretty certain effect, and biodata has a moderate, also certain effect. But the effect of conscientiousness? Turns out it's weak, and the results are really uncertain. This lets you make much smarter, more informed decisions than a simple significant or not significant label ever could. This richer output gives Bayesian analysis what you could almost call statistical superpowers. I mean, it gives us abilities that the old frequentist methods they just don't have. It lets us answer questions we couldn't even really ask the right way before.
Okay, this one is huge. Traditional p-values can only ever fail to reject a hypothesis. Basically, they can say, we couldn't find an effect, but they can never ever provide positive evidence for the absence of an effect. A not significant result is just inconclusive. It's like a statistical shrug. Bayesian methods solve this with this really elegant tool called the rope. It stands for region of practical equivalence. What you do is before you even start, you define a range of values around 0 that are so small they're practically meaningless. You're basically saying any effect in this tiny range just doesn't matter in the real world. So here's the crucial part. If your posterior distribution, that whole landscape of credible values we saw, if it lands almost entirely inside that zone of indifference you defined, you can finally confidently conclude that there's no meaningful effect. You can actually prove a negative, which is just a massive step forward for science. And the list just keeps going. Bayesian results aren't affected by a researcher's secret plans for when to stop collecting data, which is a huge flaw in the p-value system. It lets you formally build on what we already know, which is how science is supposed to work. It handles messy, complex, real-world data with ease. And best of all, the results are direct and intuitive. They actually tell you the probability of your hypothesis given the data. So this brings us all the way back to that tiny number we started with, 0.40%. Why is a field like organizational science, a field whose whole job is to understand people at work, almost completely missing out on this incredibly powerful revolution in thinking? I mean, the stakes here are actually really high. When you rely on a tool that answers the wrong question and can't even tell you if an effect is 0, it means we could be missing huge insights. Even worse, it means we might be building entire theories and business practices on statistical illusions, chasing things that aren't there and missing the things that are.
This whole revolution, it isn't just for statisticians. It's about a new way of thinking about evidence and uncertainty for every single one of us. It empowers us to move beyond this simplistic black and white world of it's significant or it's not, and to start demanding a clearer, more honest, and ultimately a much more useful picture of reality.